Hi, I will be presenting the paper Kafka Distributed Messaging System for Log Processing, which was published in 2011. There have been changes in the Kafka architecture since the paper was published, but we won't be talking about those changes as I will be presenting this paper and which was published in 2011. So this is the paper reference that I have referred to, and the presentation outline would be like what is Kafka, how is it similar to existing solutions, Kafka architecture and design principles, Kafka at LinkedIn, and finally the results and conclusion. So, what is Kafka? Kafka is a distributed messaging system which is developed to deliver high volumes of log data with low latency, and it shares the ideas with the existing messaging systems, but it also offers offline as well as online message consumption. It has the following benefits. It is distributed and scalable, it offers high throughput, and it provides API similar to messaging systems and allows applications to consume log data in real time. So Kafka uses a pull model as compared to the push model, which is used by the messaging system, which means that the producers of the message do not push the messages to the consumers, but consumers consume the messages whenever they want to. And this allows the consumer to consume the old log data or the old messages in case of failure. So this is the Kafka architecture, basic architecture, which has a topic. A topic is nothing but the stream of messages of a similar type. Produces the system that produces the messages and publishes to this topic. Broker are a set of servers which store the published messages, and consumers consume the messages from the set of brokers. So the overall architecture is that Kafka cluster typically consists of multiple brokers, as you can see in the picture on the left, and the topics which are present on the Kafka can be divided into multiple partitions, and these partitions can lie on different brokers. For example, topic 1 has partition 1 and 2. So partition 1 can be stored on broker 1, and partition 2 can be stored on broker 3. As well as topic 2 can also have multiple partitions, and different partitions can be stored across different brokers. The consumers subscribe to the topics and consume data from these brokers. So this is how the partitions of a single topics look. So the multiple partitions have the log data, and the log data on a partition is in order, and the new log data is written at the end of the partition and not in between. Um, and this is an example of the producer. So the producer has the message in the producer has a payload of bytes, and serialization can be of your choice. The producer can send a set of messages in a single request. And the consumer, this is an example code of the consumer, and the consumer creates these streams and uses these streams to consume the data from the topics. Kafka supports both the models, that is the point-to-point delivery as well as this publish and subscribe model. So this is a simple storage of Kafka, which this is a simple storage that Kafka follows. So in Kafka, the topic corresponds to a logical log. So a topic has the messages, and the messages are nothing but the log data. So a single partition, so the topic is divided into multiple partition, and a single partition has a different set of segment files which are of different, which are of similar same size. And whenever a new message is published to a partition, it is appended at the end of the last segment file. So Kafka stores the log ID as a logical offset of the log in the file instead of the actual message ID, because this reduces the overhead of mapping the message ID to the actual physical location. So how is the next message? Suppose this is the offset we are consuming now. How is the offset of or message ID of the next message calculated? It is calculated using the current message length and the current ID which we are consuming from. So whenever the producer writes to the partition, it writes at the end of the partition, and the consumer consumes multiple consumers can consume the same partition at the same time. And here is the consumer A, which is consuming from the offset 9, and here is the consumer B, which is consuming from the offset 11. And the consumers consume messages which are in order in a single partition, but if they are consuming from multiple partitions, the order of the messages is not guaranteed. And the consumer always consumes the messages in a particular partition sequentially. So the broker stores the sorted list of these offsets, which it uses later to retrieve the messages when the pull request is generated. So let's look at the efficient transfer. So producer can submit set of messages in a single send request, and the Kafka does not explicitly cache the messages, but it relies on the OS or the system page cache. So what benefits does this give? This avoids the double buffering. It remains warm. It retains the warm cache, which is used when the broker restarts, when the broker process restarts, and there is very little overhead of garbage collection. In Kafka, to send bytes from local file to a remote socket, it includes these steps that it first, the data has to be read from the storage media, then it's transferred to the page cache, from page cache to application buffer to kernel buffer, and kernel buffer to socket. This includes total 4 data copy and 2 system calls. So to optimize this, Kafka uses the send API. It explores the send API of the OS and reduces from 4 to 2 copies and from 2 system calls to 1 system call. The production and the consumption are of the data are pretty consistent and linear as it is at real time. So Kafka has a stateless broker. So the information of the consumption of the messages is not stored. The state of the messages or the consumption state is not stored at the broker, but it is stored by the consumer. And it acknowledges a particular message has been consumed. And when it acknowledges that this message ID has been consumed, that means that all the messages before that ID has been consumed. So this saves the overhead of managing the state. This stores the reduces the overhead of managing the state of every message that is consumed or not at the broker side. And to decide when to delete a message from the broker uses a simple time-based SLA that is typically a 7 days, and the messages after which are older than 7 days are deleted. The second benefit it has that the consumer can deliberately rewind to an old offset and reconsume the data because the consumer itself maintains the state of which message it is consuming. And the messages are only flushed to the disk once a certain set of messages are published to the broker and after a certain period of time. So next, distributed coordination. So let's look how the coordination works in the distributed system of Kafka. So each producer can publish a message to randomly selected partition or a partition which is semantically determined by a partition key and a partition function if any present. Kafka has the concept of consumer groups. Every consumer, all the consumers are present in groups always. It can be a group of 1 or group of n, and each consumer in a particular group is supposed to consume or consumes a message from a single partition, means or a message from a single partition or a topic is consumed by only one consumer from one consumer group. So there is no coordination which is needed between the consumer groups, which reduces the complexness of locking and state maintenance between these consumers. And for the as there is no central master node in Kafka, instead of consumers consumers coordinate among themselves to facilitate the coordination, Kafka uses Zookeeper. So the Zookeeper is used for cluster management as well as failure detection and recovery. It is used for detecting the addition and the removal of the brokers and consumers, triggering the rebalance in the case of failure, maintaining the consumption relationship, and keeping the track of consumed offset of each partition. So what is cluster management? Cluster management is like Kafka, the Zookeeper. In cluster management, the Zookeeper, whenever there is a broker or a new consumer that starts, it has to register with the broker registry and the consumer registry on Zookeeper. So this is how cluster management is done. The broker registry contains the broker's host name and a port and set of partitions and topic sets is stored on it. And the consumer registry includes the consumer group to which the consumer belongs and the set of topics that these consumers subscribe to. Each consumer group is associated with the owner registry, where the part to the subscribed topic and the value part of the subscribed topic is saved, and the value is the ID of the consumer which is consuming to this topic or partition. And there is offset registry which saves the last message offset which was consumed from a particular partition. And then if there is a broker fails, all partitions on it are automatically removed and from the broker registry. The failure of a consumer causes it to lose its entry in the consumer registry, and all the partitions to which a particular consumer owns is lost. So the consumer registers a zookeeper watcher on both the broker registry and the consumer registry and will be notified when there is a change. If there is any removed from the broker set or a consumer removed from the consumer group, in this case, it can initiate a rebalance process. There is as well there is one more process where if the broker fails, then how the partitions are moved to the existing or available brokers, which is not discussed. But from my research, from different videos and blogs, that is, I could understand that there is also a rebalance between the brokers, which is in the new version of Kafka. The rebalance algorithm is as follows. First, the available partitions are calculated, then the available number of live consumers are calculated, and then the n is calculated, which is the number of partitions which are available divided by the number of available consumers, and then these n partitions are then divided among the available consumers. So delivery guarantees. Kafka guarantees at least once delivery, that a message is delivered at least once. Kafka guarantees that messages from a single partitions are consumed in order, but from different partitions, there is no guarantee of ordering of messages. If a broker goes down, any message stored on it yet consumed, which is yet not consumed, is unavailable. And if the storage system on the broker goes down, unconsumed messages are lost forever. So Kafka at LinkedIn. So let's look at the architecture of Kafka at LinkedIn. So there are two clusters of the Kafka. One is present on the part where the real-time services are working. So the front-end services generally generate the events or the log data, and then it is published to the brokers, and the messages are load balanced among the brokers by the load balancer. There's another cluster which lies near the data warehouse or the Hadoop location, which pulls the data from the cluster which is at the live location, and then it loads on the data warehouse and the Hadoop, which is used further for offline analysis. And at LinkedIn, Kafka uses Avro serialization technique for serializing its messages at the producer side. So, in conclusion, there was an experiment which was done during this paper, which compared Kafka with RabbitMQ and Apache ActiveMQ. The producer test of the messages. In the producer, there were two tests, the producer test and the consumer test. In the producer test, it was observed that Kafka produces messages in order of magnitude as compared to ActiveMQ, and two times more than RabbitMQ. This is because no acknowledgement from broker. So broker doesn't give any acknowledgement or doesn't wait for any acknowledgement. It is a time-based SLA which is used to delete the messages on the broker, and the consumer keeps the track of the messages consumed by the consumer instead of the broker. So this is a benefit. And second is the simple storage format that we had seen in the previous section. The second is the consumer test. Kafka consumed 4 times more messages than the ActiveMQ and RabbitMQ. This is because the ActiveMQ and RabbitMQ, both the messaging systems, maintain the delivery state of each message, and writing to the disk consume more time in this message systems. So at the end, I would say that these unconventional choices which were made by Kafka architecture design make it more efficient as compared to the other messaging systems. These are the references. This is the reference paper that I've referred to. Thank you.